Hello everyone, my name is Wu. I'm glad to introduce our work NetLLM. This is the work that we focus on using large language models to solve networking problems. Now let's get started. Well, this presentation has 4 parts. And in the first part, let's first discuss why we start this research. Well, deep learning has been popular in networking. It has been applied to solve complex prediction and decision-making tasks in networking. And this figure shows the typical pipeline of the DL-based algorithms. We first need to design a deep neural network. Then we have a dataset or network environment to train the DNA model. And after training, the DNA model can solve the networking problems, so we can deploy it for the network service. Unfortunately, although there are so many DL-based researches in networking, they still suffer from several limits. The first is their success heavily relies on the manual design of DNA models. Unfortunately, due to the black box nature of the DNA model, the design process is done in a trial and error manner. That said, we need to handcraft a DNA model, then validate its performance. And if it doesn't work, we need to modify the DNA architecture. And this process will keep going until we find a good DNA architecture that works well for the network service. So the entire process can be labor intensive. And to make things worse, DNA is not shareable across different tasks. For example, if we have a well-designed DNA model for the adaptive array streaming service, we cannot use the same model to do cluster job scheduling. So this means that one DNA only works well for one task. So we have to design specialized DNA models for different tasks. And this will increase the model engineering overhead. The second limit is that the DL-based algorithms tend to achieve poor generalization performance on unseen data distributions or environments. For example, in this figure, if we train the DNA on the stable network environments, it tends to achieve good performance on the same environments, but it tends to achieve poor performance on the unseen fluctuating network environments. So to address these limits, we start to think that can we use one model for all networking tasks with even stronger generalization? And we think the recent large language model could be the possible answer. So let's talk about what we try to approach in this research, and that is NetLLM to networking. Well, LLM has been popular in recent years. It has been pre-trained on massive data to absorb extensive knowledge. Then it can serve as the foundation model in natural language processing. In other words, we use a single LLM to achieve one model for all tasks with even better performance. So yes, LLM is powerful in NLP, but can we use it in other domains? Of course we can. Well, researchers have recently shown that LLM is not just a master in NLP, they can be applied in other domains successfully. This is because after large-scale pre-training, the LLM has some emergent abilities, such as planning and generalization to unseen cases. And these abilities prove to be transferable across domains, as this allows the LLM to be applied in other domains such as robotic control, chip design, and protein structure prediction. And that's impressive, but is it possible to use LLM for networking? Of course we can, and that's what we do in this paper. So why should we use LLM for networking? There are some certain benefits of doing so. First, we can use one LLM for various tasks for networking. So this means that we no longer need to handcraft specialized DNA models for different networking tasks, and therefore we can significantly reduce the model engineering overhead. And second, with the extensive knowledge of the LLM, we can utilize its powerful capabilities to achieve better performance on each task. So in this paper, we try to answer the following key question. Can we efficiently use the LLM to achieve one model for all networking tasks with even better performance? And we believe the answer is yes through our framework NetLLM. Let's discuss the idea of NetLLM. Well, NetLLM is the first framework to adapt the LLM to solve networking tasks with low efforts. This means that while the LLM is originally designed for NLP, the NetLLM can wrap the LLM to make it useful for networking. And it consists of the following three modules. The first part is the multimodal encoder. It allows the LLM to understand the network information effectively. And the second part is the networking head. It allows the LLM to generate answers for networking efficiently. And finally, there is the data-driven low-rank networking interpretation scheme, which is used to fine-tune the LLM to learn networking knowledge efficiently. And first, let's look at the multimodal encoder. A key challenge here is how to enable the LLM to understand the networking knowledge, networking information. Well, in fact, we know that in networking tasks, we often collect various pieces of information for decisions. For example, in bitrate streaming, we often collect network throughputs for bitrate decisions, which are represented as time series data. However, this multimodal network information differs from plain text, the naive modalities supported by LLMs. So we cannot directly use the LLM to process the networking information. And to address this challenge, we designed the multimodal encoder. Our key idea is to project the multimodal data into the same feature space as text, so that the LLM can understand the multimodal networking information. And inside this module, we first use the existing feature encoder to inject features from the raw input data, such as vision SIGCOMMA for image and graph neural network for graph. Then we use a linear layer to map the injected features to the same feature space as text. And finally, we add a layer normalization layer to build the multimodal features to improve the training stabilities. And this will result in a set of test-like features that can be understood by the LLM. And the next challenge is how to enable the LLM to generate answers for networking efficiently. And to understand this challenge, let's first discuss the answer generation mechanism of the LLM. Well, in fact, the LLM generates answers by token prediction with a language modeling head. Let's look at a concrete example. The generated token is repeatedly fed to the LLM, and the output features of the LLM are fed to the language modeling head to predict the next token. And this process will keep going and going until we have a special token called end of sentence token is predicted. Well, why this paradigm is well suited in NLP, it presents some limitation in the field of networking. First, from this figure, we can see that it takes multiple inferences for the LLM to generate a single answer. So this can result in high generation latency. Besides, due to the uncertainty of token prediction, the generated answers could be embedded. For example, in this figure, the generated bitrate does not match any bitrate versions of the encoded video. So we cannot use this bitrate to download the video chunks. And our idea to address this challenge is to replace the language modeling head with our customized task-specific networking head. And the networking head is in fact a linear output layer to directly generate answers based on the LLM output features. And let's look at a concrete example. Well, we feed the output features of the LLM into the networking head, and we can design the networking head to directly generate the probability distributions of the possible bit rates. Then we can sample a bit rate from the bit rate distributions. Then we can use this bit rate to download the video chunks. So why this approach is simple? We can see that it can indeed generate answer in a single inference, so it can reduce the answer generation latency. Besides, it can also guarantee the validness of the generated answers. And the final challenge is how to fine-tune the LLM to learn networking knowledge efficiently. Well, unfortunately, the cost of fine-tuning the LLM are expensive because of the large parameter size. And the reasons are twofold. First, well, we know that reinforcement learning is widely used in networking. However, it requires the active interaction between the environment and the LLM to collect experience datasets for training. So this figure illustrates the timeline of the RL training. So if we use this timeline to fine-tune the LLM, we will spend a lot of time on having the LLM to interact with the environments to collect the experience dataset. This process can be very time-consuming. And to make things worse, if we choose to fully fine-tune the parameters of the LLM, the training time can be even more expensive because of the large parameter size of the LLM. So we designed the DDL-RNA scheme to address this challenge. First, we remove the interactions between the LLM and environments based on the data-driven RL. To be more specific, we use an existing non-LLM policy to interact with the environment to collect the experience dataset. And once the dataset is collected, we use it throughout the training process to fine-tune the LLM. And this process can lead to the reduction of more than 30% of training time. And next, we also insert some low-rank matrices to reduce the number of trainable parameters. The insight behind is to constrain the parameter update to a limited amount of parameters. So this approach can significantly reduce the training time with a reduction of more than 15%. Finally, let's discuss our evaluation results. Well, in our experiments, we used 3 example cases to evaluate the performance of our framework. That is pupil prediction, adaptive behavior streaming, and cluster job scheduling. And we compare our framework with 3 other state-of-the-art algorithms on each task. And we use the Llama 2 7B as the default LLM. Well, in the first part of our experiment, we test the performance of each method when the testing distributions are the same as training distributions. And we can see that the NetLLM adapted Llama 2 significantly outperforms all baselines across all tasks. And this demonstrates the effectiveness of our framework in adapting the LLM for networking. And it also showcases the promising potential of using a single LLM to achieve one model for all tasks with even better performance in networking. In the second part of our experiments, we evaluate the generalization performance of each method. And we can see that the NetLLM adapted Llama 2 still outperformed all baselines across all cases. And this indicates that with our framework, we can indeed efficiently utilize the extensive knowledge of the LLM to achieve stronger generalization. Next, to understand why the LLM can be useful for networking, we investigate the importance of its pre-trained knowledge. To be more specific, we remove its pre-trained knowledge by randomly setting the model parameters of the LLM. Then we compare its performance to the regular case. And we can see that without the pre-trained knowledge, the performance of the LLM significantly decreases. So this indicates that the pre-trained knowledge of the LLM is important. And the LLM indeed contains some common knowledge that is useful for networking. Next, we investigate the impacts of different types of the LLMs, and we can see that all the adaptive LLMs outperform the state of the task on different tasks. So this indicates that different LLMs can be adapted to solve networking tasks with our framework. And finally, we investigate the impacts of the model parameter size of the LLM, and we find an interesting phenomenon. Well, when the parameter size is less than 1 billion, we find that the LLM only perform well on one task but poorly on the other task. So this means that it no longer generalizes across different tasks. So the 1 billion parameter size could be the bottom line of using the LLM for networking. Now, at the end of this presentation, we can answer some key questions. First, can we use the LLM to achieve one model for all networking tasks with even better performance? And the answer is yes. Our framework NetLLM can do that for us. And is our framework NetLLM applicable to various LLMs? Of course, our framework is compatible with different LLMs. And is this the end story of using LLMs for networking? Well, of course not. We know that NetLLM is not the final solution, and we hope that it can inspire more researchers on LLMs for networking. And this is all about our presentation. Please feel free to check out our paper and GitHub project. Thank you.